Welcome to breadboarding. In the previous video we looked at how we could eliminate the CGA snows. This is the artifacts we get on the screen here as a result of the CPU updating the video RAM whilst the CRTC chip is actually accessing the memory for the display. And we came up with a number of changes for the writing of data to the video RAM here, where these areas in orange are really where we need to make our changes. A new programmable logic device, CGA Logic 3, and some changes to the 1 and 2, and also for the read where we were going to have to do some similar changes and also potentially add some wait states to the memory read accesses so that there was sufficient time for the CPU to read the data from the video RAM. So in the schematic we're going to need to change the CGA Logic 1 PLD, Logic 2 and Logic 3 is the new one, and we're also going to need to change these two address latch chips from 573s to 574s, and then we're also going to need to then change the wiring on the video RAM and on the 74LS 646. So here's the board as it is at the moment. So we're going to need to pull out this chip and reprogram it, swap out these two chips here beneath the cables here for the 574 equivalents. We're going to need to add another breadboard down the side here and update this particular PLD with the new version and wire in all of the new chip into all of the other signals and things around here. So I'm going to go off and do that. I'll commentate over it and we'll speed it all up. Then hopefully when we come back from that, we're in a position to start up the CGA card and breadboard PC and see whether or not we've made a difference. So add the extra breadboard, then swap out the Breadboard Buddy power connector there. Then program the CGA Logic 1 PLD and replace the chip label. Put that back in. Unplug the connections are now handled by the other PLDs. Now replace the 573 buffer latches with the 574 versions. Now program CGA Logic 2 PLD and replace the chip label. Put that back in. Now I need to update the CGA clock PLD, a few corrections there. Disconnect some of the hookup wires that are going to be replaced in the new configuration. Now locate the CGA Logic 3 PLD, which is going to do most of the control signals. Put in the power and decoupling capacitors, and now we're just going to disconnect a lot more of the cables. Check off the schematic, the changes we've made. We're going to select AB, select BA and direction. Then the video RAM write and output enable. The CAB and CBA clocks and the 646 output enable. And that's the graph connection as well. That's CGA RAM. Now the clock and the interconnects between the two PLDs. This version we were using the CPU clock, so just wiring the CPU clock there, and we're then going to be wiring in all the memory read, memory write, IO read, IO write. The IO read, IO write aren't needed down the bottom here, but they are needed at the top part of the board. Just check those off. Need to remember high res and the CRTC video address enable, CPU address output enable, and the clock for the CPU address as well. That's the high res from the control port. Check those off. So now need to do the clock QABC from up in the clock PLD and the dot clock, and then check everything off. So this is the CGA card in its current state. There's a number of logic analyzer leads all over the place, so it does look quite messy, but these are mainly test leads and things here. Now I've gone through a number of days testing this and tweaking it, and what I'll show you is the result of that. So what I tend to do when I'm doing this, I'll take screenshots of the logic analyzer output at various stages, particularly before I make any changes. I tend to put comments and things on there. Now, some of the time I don't leave these behind and show these in the videos, just really to remind myself of what I've been doing. Now, what I've got here is a number of these screenshots and things, and I'll just go through them very quickly. And you can see that there are a number of things I've gone through diagnosing the different changes and things to the card. You can see here that some of the timing for some of the signals and things wasn't quite right, so we need to adjust things by perhaps extending the anti-snow period here, going through various other changes in the rules as we got here, and sort of evaluating the different changes. And basically the test screen I got was looking like this, which was not particularly great. So I went through some more changes, more changes, more changes. Then the clear screen, which was coming out quite messy, is better, but it still has some artifacts there, so it wasn't quite right. Did a few more changes, few more, another one. Particularly here, this is the wait state, so we can see here this is a normal read period, and this is where the wait states have been extended by way too much, but this was testing the wait states. Changes to the various rules in the PLDs, more changes. Some issues here was looking into, some more changes. And this was really where I left it. So this screen is still not quite right, and you can still see there's artifacts all over the place. So I decided to stop. When you're in a hole, stop digging. So what I decided to do is have a look back at the Nanocomp 6809 project I did probably a year, 18 months ago. And there were two videos I did there on fixing snow. So the Lunar Lander game, the Tetris game, and another test screen I had here. You can see here that there is some evidence of snow. And over these two videos, I actually managed to fix most of that. So I went back to those videos, and really just to summarize the key things out of those two videos. And then the first video, by analysing all the signals, what I looked at is the clock signals which are used from the dot clock. So the dot clock is 25 megahertz VGA dot clock is divided by 2 for QA, divided by 4 for QB, and divided by 8 for QC. And QC also provides the character clock for the CRTC. And what I did is I analysed when the clock cycle for the video card was interacting with the E-clock signal for the 6809. So the E-clock signal is related to when the CPU is actively accessing the memory, whether it's reading or writing. And you worked out all sorts of periods and things here, and you'll see that because the video phases that we've got here will vary depending on when the video phase and the CPU phase occurs. And so this is one of the reasons why it's so difficult to actually try and fix this problem, is because the two clocks are out of sync. And then in the second video, all of that output was then summarized in a table like this. So we have really the dot clock cycle. So this is the video cycle that the E signal was in when it started from 0 to 7, and there were various cycles that we're using for configuring the PLDs to generate the right timing. So what I decided to do was do my own analysis. So I watched both the videos, reminded myself of what I did, and I recorded traces like this for various video modes, and I analysed this to look at the data. If you see here that we've got the memory read signal here starts at A1, and here we've got the QA, QB, QC, QD. So this is evaluated as cycle 0 through till A, B, C, D, F up here. And so what I've done is going through each of these cycles. So this is cycle 0, cycle 1, you can see cycle 1, cycle 2, cycle 3, cycle 4, cycle 5, cycle 6, cycle 7. And also there was another situation here where under some circumstances the video write enable was missing as well. So having gone through and analysed all of that, I produced a diagram similar to the previous video. So this is just being done for this CGA card. So you see we've got the QA, QB, QC clock signals there with the video phase. I've also got the character latch and the attribute shift register latch. And you can see here that the attribute latch for the 4-color graphics mode is in fact appears at the end of cycle 7. And these green dotted lines, the cycle 2, which is our anti-snow cycle, there's also actually another cycle around cycle 6 as well. And what I've done is I've highlighted in the green dotted lines here where these cycles actually provide a clean period for actually updating the video RAM. So the long shot of all of this stuff is from doing this analysis and also doing the analysis for the reading as well down the bottom here. I've now got a CGA version of this, so rather than being based on the 6809E signal, basing this just on the cycle, so cycle 0 to cycle 7 of the video phase, and then the CAB address clock and the output enables that are driving most of the buffers and latches and things, and then the video write enable and the clock BA, which clocks the video RAM data into the buffer to be read by the CPU. So by doing all this analysis, what I've been able to do is to streamline doing this so it hasn't taken half as long as it took me the first time round. And what I'll do now is just to explain what these changes actually involve doing. This is a summary of the two videos then and applying it to our PC CGA card. It's a 6809 nanocomp anti-snow approach. It made use of the 6809 E-clock signal. So the E-clock signal is active during reads and writes, and there's a separate read-write line which tells you whether it's reading or writing, whereas the 8088 and 8086 have a active low memory read and memory write. So if we take the inverse of memory read, memory write, and all them together, that gives us the equivalent of our E-clock signal, which I've called it CPU activity, CPU act, which means we've got the CPU actually doing something with the video RAM. So then we've got our video clocks. So the QA, QB, QC, QD are the video dot clocks. That's a 25 megahertz VGA clock divided by 2, 4, 8 and 16. For the moment we're going to ignore QD because that's only used for the 40 column mode. And then what we do is we latch the QABCD values to CQABCD when we start the CPU activity. So that basically gives us a cycle, potentially C0 through to CF. And that becomes important when we start to try and work out the timing. So that tells us really which video cycle the memory access is actually starting on. And also what we do is we count the current dot clock cycle from the start of the CPU activity, and we keep that count in dot clock Q0, Q1, Q2 and Q3. Then what we can use in the programmable logic device configuration using the CUPL field syntax, we can actually define two cycles, so the cycle Q cycle and the dot clock cycle. So CQ is the video cycle at the start of the memory read or memory write, and the dot clock cycle is the number of clock cycles since the start of the memory access. So then the PLD conditions actually then become relatively straightforward. So you can say that when we're in cycle 0 or cycle 4, then we need to only make a signal active during cycle 5 and cycle 6. And also if we want to make it a sort of a half width, then we can actually combine that with the dot clock or the clock signal in fact. Now the only issue here is we need to make sure we don't end up with too many terms for the PLD pins. So the number of conditions that a given pin on a program or logic device can do varies between about 8 and 16 I think on the ones we're doing, and so some of the pins in the middle of the device tend to allow more rules than the ones at the end of the device. So this is one issue that we need to be aware of. So then take a look at the PLD configuration from the original nanocomp. So this is the video snow PLD, and we can see here that we've got the QABC input dot clock, and we've got our latched QABC And we've also got a gated dot clock. So the dot clock is actually controlled by the E signal, so it only clocks whilst the CPU is active. So these rules are relatively straightforward. All we've got really is the latching of the QA, QB, QC there. And then the other PLD is more complex. And you can see here that this actually takes the E, QA, BC signals coming in from the other one. And then it also has this dot clock Q0, 1, 2 and 3. So this is the counter really determining which is the current cycle from the start of the current memory access. Now the clever bit in here is the defining of the 2 cycle terms. Now the main issue you've got to be aware of here is that these values use hexadecimal, and I got bitten the first time around in that I had 1 0 and I thought that was for 10, and in fact I should have been using A, and that caused a few problems. We can see down here that the video read-write signal is made up of which cycle and the dot clock cycle we want, and these rules basically generate the control signals that we need to be able to fit the video reads and writes in within the sequence that will allow our video accesses to avoid generating snow. So these rules are now being carried over into the 2 logic devices that we've already got. So if we go back and have a look at the diagrams and see what changes we need to make, fortunately there's very minimal changes were needed. So this is the write diagram, and in fact we don't need any more CGA logic devices. CGA logic 2 and CGA logic 3 are the main ones that we're actually using here. I've already gone through and changed these latches here and done the changes for this one, so we did that already for the previous lot of changes. To actually fix the issues that we've got, I only need to really rework some of the rules between here and here. And there's a slight difference in that our CPU activity and direction are still things that we're using here, but we've now actually got these QA, QB, QC, QD values which have now been latched when the CPU activity starts, and these are then used by this to actually determine all the timing. And on the reading, similarly, I think this signal now, rather than coming from this one, comes from this one. So basically all the control logic is now coming from here, and this actually will handle all of the timing that we need for the various output enables and the latch and clocks and things like that, particularly for the video data buffer and the video RAM. So if we take a look at the rules now, the CGA Logic 2, this was one of the original PLDs. I've now created a version 10, which is for this revised approach. You can see that we've gone through a number of different versions. I was trying to resolve the issues and things. Some of the pins are the same that we had previously, but then we've got some of the new pins. So these are the clocked QA, QB, QC, QD from when the CPU activity is triggered. So CPU activity is when either memory read or memory write and we're accessing the CGA RAM. There's definitions for some of the other pins here, which have been consolidated and simplified. And then we've got here that when the clock occurs, so the clock signal here is going to be connected to CPU activity. When the clock occurs, then the QA, B, C, D value is latched into this value here. What we also do is we gate the dot clock with CPU activity. So that means that the dot clock only counts during the active period of the CPU, and the direction will also be set to 1 for memory write when we're accessing CGA RAM, and it will be 0 the rest of the time. So that's the first PLD. The second PLD is more complex. So this has the latched QA, QB, QC, QD values coming in. It also has the CPU activity coming in, the direction, and also 2 of the control port signals to determine whether we're in graphics mode, text mode, or high-res mode. And then you'll see here that the dot clock Q0, Q1 and dot clock Q0, Q2, I've put those on the outer pins here. These are the ones that have the least number of terms, and we'll see when we look at the documentation output for this chip here where we can find that information out. And these ones in the middle are the ones that actually require more of the terms to be able to work out what the signals are. And you can see here by defining our CQ cycle, so CQ cycle is defined by the CQD down to CQA, and our dot clock cycle is defined by dot clock Q3 down to dot clock Q0. we clear this dot clock count whenever the CPU activity goes low. So when the read or write finishes, then this dot clock cycle will be reset to 0. And this is a fairly standard set of rules that you use for counters and things with the flip-flops in PLDs. Now these sections here, we may need to do something like this if we run out of combinations and rules for the rules. In the original nanocomp one, I actually need to create some intermediate terms which would actually calculate these values here, and then these values are included in the rules below. Although this one here, I think, has got to about 16 terms, I think, which is the limit. So if we run out of cycles here, what we can do is to combine some of these combinations here into one value and substitute a value there into here for that sort of section there, and that will reduce the number of terms we need. So basically the rules that we've got here are encoding these rules here. So we want our CAB or address clock to be on dot clock cycle 3, and then the output enables and the video write CBA clock need to be on these different values. And in fact there's 4 different groups. So I've got group A, group B, group C and group D. So this allows us to group together C0 and C4, and similarly for all the other ones. So you can see here that when we've got C0 and C4, then we want the write to occur on cycle 6, and because we're combining it with the dot clock, then that will narrow the pulse down to 20 nanoseconds, which is what we need for the video write. And then for the output enables, then in fact we've then encoded these rules. So you can see CQ0 and CQ4 will be between clock cycle 5 and 6, and we'll only use the second half of cycle 5, and similarly for these other ones. Now when we compile all of this using WinCUPL, the documentation file will expand all of these terms. You can see how many terms for the address output enable has been expanded quite a bit, and the video write enable has got about half the number of terms there. And then this symbol table is quite useful because what it indicates is shows what the number of terms we've used are versus the max terms. And you can see here that the max terms is 16 and the terms used is 16, so we're actually right on the limit there. Whereas our video write enable, max terms is 16 but we've only used 8. So if we were to run into a problem here, what we'd have to do is to calculate an intermediate value. So an intermediate value like one of these things here, and that will allow us, by pre-aggregating these values here, we can actually reduce the number of terms we need. So I've programmed the PLDs for these. Now what we need to do is to wire this up. So I'll just have a look at the KiCad diagram. So in fact the KiCad diagram hasn't really changed that much. A few of the signals have changed, but in fact the main changes we need to make here are to this PLD, and how this is wired up between these chips. This one up here hasn't changed. These two here are the same, and the only thing we really need to worry about is the various control signals coming from down here. And you'll see now that I've updated all the pin layouts here, so it's still got a lot of the clock signals coming in here, but most of these signals up here have changed, and there is an interaction between these two PLDs because we've got the different clocks being used here. Then this is a main limitation of this type of PLD. You can only have one clock and one reset signal for each PLD. So what we're going to do now is to replace these chips. We'll unplug all of the logic analyzer output, put on new labels. So I've done some new chip labels for these two chips. So these are the previous versions and these are the new versions. So you can see there's quite a few changes on the right hand side. The left hand side is less different over here. So I'm going to pull out all of the logic analyzer leads that we've got here, and I'm going to pull out most of the wires around these two chips because I think we're going to need to rewire all these. A lot of the stuff up the end here is going to remain the same. So I'm just going to go off and do that, and when we come back hopefully we'll be in a situation to run the card and to prevent the video snow from occurring. So just going to disconnect logic analyzer and the various other hookup wires being replaced. memory read, memory write, CGA RAM, and the IO read, IO write were some of the wires which are left hanging there for the moment. Update the rules for CGA Logic 3 and update the rules for CGA Logic 2, also replace the chip labels as well. I wired in the CQA, CQB between the two PLDs off camera there. So then DIR, video RAM output enable, and the 646 output enable. Then video RAM write enable and CPU address output enable. So now IO read and IO write are no longer connected to the PLD down here, but they are needed to be connected up the top of the board up there. So dot clock, CPU address clock, CAB and CBA. And then high res and graph from the control port. Okay, so that should all be the changes wired up. So what I'm going to do now, I'm just going to plug in my 32-way logic analyzer. So I'll hook this up and then we'll try and run things. I suspect we'll need to make a few changes before it will work. But when we come back, hopefully we'll have something updating the video without any snow. Okay, so here's the current state of the board. You still see there's quite a lot of logic analyzer signals all over the place here. Now we do actually have one more chip. So these are the two PLDs we were talking about earlier. Needed to add in an extra flip-flop here, and that basically is allowing us to delay some of the signals by up to 2 dot clocks. We didn't have enough pins on the PLDs, so what I'll just quickly show you is the changes that we made. So this is the page where I summarised what the nanocomp snow removal approach was, but there's a few things we had to do here. First of all, this CPU activity, you needed to sync it with a dot clock, because sometimes what would happen is the particular cycle would only be a few nanoseconds. So by syncing it to the dot clock, we would make sure we always have a full 40 nanosecond dot clock period at the beginning. We also needed to simplify some of the rules. So in fact, we only needed to have 4 different cycles within the timing, so we're able to take out some of the latched QC, QD values, and in fact in the end I put in the high res signal into this sort of cycle timing that allowed me to separate out the 40 column mode from all the other modes, which simplified the number of rules exceeding the PLD terms. Also needed to add that flip-flop, and this is because the CPU activity needed to be delayed by a couple of dot clock cycles, in particular when the dot clock that was used to clock these things was getting stopped too early, and so we're sometimes missing a cycle. So the field definition here now has the high res, the A and the B, so that we can include the mode 0 40 column text. And now the rules are a bit simpler because we're not worrying about 8 cycles, we're only worrying about 4. Then they've been simplified sufficiently that we could include the rules for mode 0, mode 4. So that's 40 column mode and the 4 color graphics mode. They also needed to include wait states. So this is from the 8088 datasheet and just shows that the ready input must go low. And in fact, the way how the wiring works on the original 8088, there's the ready wait signal, and if wait goes high, in fact, then it will set ready to be low. So basically, if we set wait to be high during the early parts of the read cycle, it will actually extend the read cycle by 1 or more clocks. And as a result of doing all these changes, this is what the mapping information was originally, with all these various cycles, and then what we've ended up, we can ignore the lower 4 cycles, and then some of these values have changed. Generally, these values changed because we were syncing the CPU activity value, then that tended to delay it. So we need to bring everything back a cycle. But these now values seem to produce pretty reasonable video output. It's not perfect. There's 1 or 2 minor issues I need to work on. So let's take a look at the video outputs when I run the test programs. So this is the first of the test programs. So the first thing it does is clears the screen. So this, in some of the earlier slides, was showing that it wasn't updating all of the video data quite correctly. Then this is our 80 by 25 test screen. That seems to be coming out okay. Do still occasionally get the odd attribute, the odd byte that doesn't quite get set properly. I think I know the reason for it, but it's down to the fact that the write signal that's using here is getting quite narrow, down to about 12 nanoseconds in some cases. So I need to do a bit of investigation to expand that up to about 20 nanoseconds. Flashing. The 40 column mode is now working okay. Then the next test screen clears the mode 4. Now this still has a few minor bits that are not coming out quite right. So this is the 4 color graphics mode, and then this is a test pattern that I used to check to see that all the values being written okay. This is the one for the high res graphics mode, black and white, and that seems to work a lot better. Then there's another version of this program I've got where basically after actually checking each value we've written, it then overwrites it with 0, so that the only bits we would actually show on the screen here would be where there's been a problem reading or writing. And this is the revised version of the screen. So what this will do is only leaves the bits there where there's been problems reading and writing to the RAM. So the mode 4 is a lot better than it was, but it still has a few issues, which I think this timing that I was telling you about would probably resolve. Then this is the black and white mode, and then you can see there that in fact there are no wrong bits there. So this is actually completely black, so that means it's a successful test. So if I remind you of the snow screens we had previously, so this was the main screen from the CGA comp test program that would provide quite a lot of interference on the screen of snow. So we'll just run that one up first. This is a snow test function, so just run this and we shouldn't see any of that sort of green stuff we saw in the previous slide. You see there's no snow appearing there. The odd character does get corrupted when it's running for a while. If I left this running for a few minutes, and you'd see that there'll be more and more of these characters. The actual snow situation is much better as just this timing issue with some of the reads and writes. So here we have GW Basic. We're just going to load samples.baz. What we can do, if we just list the program here, originally this would produce lots of interference as it scrolled, and now the interference is very much eliminated. Occasional odd attribute that gets corrupted. Now if we run this, and the art one was the one with the city. And you can see now the snow is largely gone. There's 1 or 2 pixels that suffer this video RAM timing issue, but the actual snow has all gone. And if we look at ball, so you can see that the snow has gone, but there are occasional timing issues that result in the pixel getting left behind. I think it's probably related to the reading and then writing of the pixels. So the snow's gone, but there are a few timing issues still to be resolved. And then finally circle. So you can see these circles here that I've speeded up the earlier part, but you can see there's very little interference at all. Occasional bits don't quite get set properly, but the actual snow has largely been eliminated. Then the final one was the CT test utility. This showed the interference that we got on the screen in the high-res graphics mode. Now you can see the direct writes here are actually coming out much better, which makes me think it's probably related to something when the BIOS is being used and it's reading then writing the data. There's some sort of issue there, but in general it's actually coming out a lot better than it previously was. So compared to the sort of snow interference we had there, then that's a big improvement. So I'm going to break the video there. What I'm going to be looking at in the next video is running Windows 1.0, and we'll also try and hook up the PS2 mouse and try and get the mouse working. It is possible to run Windows without the mouse, although it is a little more difficult than it would otherwise be. I've also been doing a little bit of investigation. Unfortunately, the CGA enhancement, the drivers for Windows to use this sort of high resolution video graphics adapter only supported the 286 from what I can tell. So at the moment I'm not going to be looking at doing that, and what I'm going to do is to go off after I've done the Windows and actually have a think about what to do next. So what I might do is to actually rebuild this and eliminate some of the mistakes I made along the way and actually improve some of the things, and then perhaps after you've done that I might look at doing the same sort of thing with a 386. So I'm going to finish the video there. So I've been able to eliminate the video snow pretty much. There's an odd little artifact left behind through video RAM update timing, which I'll look at in the next couple of days. If you don't want to miss out on future videos, if you'd like to hit subscribe and click like as well if you found any of the content interesting. Thanks for watching. Next video we'll be looking at Windows 1.0 on the Breadboard PC.